Algebra. Once you start getting involved with it, you start dealing with fun numbers, which are actually letters. Kids love it, right? But something interesting about algebra. Say, you might want to express some quantity. People like to use x. When you write, God, why don't you focus? When you write x on the page, it represents something. You may not exactly know what it is yet, but even though you don't know what it is, there's certain things that you can constantly do and not really worry about it, right? So that was good. X, you can always add 0 to it. Doesn't matter, what side you happen to use. You'll still get the same thing, and you can multiply 1 by x and still get x there. So no matter what x is, whether it's infinitesimal or infinite, these basic operations apply. Now, you can think about that then as that there's always sort of an identity operation being applied to any expression that you make on the page. This is sort of a strange way of thinking about number, but I think it's useful to keep in mind because that was sort of part of the inspiration for the algebra forms. Now, the algebra of forms is kind of came out of the laws of form, so I did a quick little intro trying to explain what that's about. You should definitely check that out if you want to know more about it. And in the laws of form, you have these two symbols, really only just one and then itself twice, right? But this symbol is something like a negation operator, and it works really well for Boolean logic. But what about when you're trying to create an algebra with this sort of thing? Things become a little bit more complex because the rules that you learn for the world of logic are not exactly the same in the world of algebra. So in particular, while in logic, saying a statement twice is as good as saying it once, in algebra, your statements are not simply information, but represent functional operations on things. So doing something twice is not the same as doing it once under most circumstances. There are exceptions. And so in the context of multiplication, right, this is really this familiar x squared thing, which you know and love. So, in terms of algebra, your rule of duplication actually immediately gets you to exponentiation. It's something that you have to work with. Similarly, the rules for negating have changed. So here, whereas before the variable state is defined by contradiction, in algebra, in general, x is not equal to negative x. And so, but the act of negation itself is something which changes the sign in which you're using. So, so really, there's nothing groundbreaking here or terribly different than traditional math. It's just sort of an alternate representation system. There's jump cut. So part of the motivation behind this algebra of forms, so just like the laws of form is a simpler way to represent logical systems, what we really wanted is a simple way to represent algebra, and that's a statement which probably deserves some qualification, but I guess what we really want is for form and function to make some kind of appearance within the algebra, within the symbols that we use for the algebra, right? So, this is a fine symbol, so like x equals 1 to infinity of something, right? So, in general, it doesn't really matter what symbol we use, that we use sigma for summation, but what if you came up with a symbol that really captured what summation is doing? Wouldn't you want to use that instead of a sigma if you had it? That's the idea. If we use squares a lot, right, as well as other powers of numbers, but we don't often use triangular numbers, and you know what triangular numbers are even though you don't remember them. So much like square numbers can be arranged in a lattice, triangular numbers can also be arranged in a triangular lattice. right? So typically you'll find, and I'm actually going to make a distinction between sort of two forms of triangle function. So we'll think about sort of the up triangle and the down triangle, right? And this is defined pretty simply. You can look up triangular numbers, nothing new here. X squared plus x over 2, alternately x squared minus x over 2. Both of these give you triangle numbers. There's sort of an offset between them, but otherwise there are certain kinds of symmetries associated with them. In many cases, triangle of negative x is something like down triangle of x, or you can offset these things by 1, so x minus 1 is equivalent to down x, right? These rules may not hold under all circumstances, but in general, there's this symmetry between the two, right? You can calculate sort of what their values are. So when x is 0, they're both 0. When x is 1, down triangle is still 0. And then after that, you start to get the rest of your sequence. So they're mirrored around 0, but it just so happens that what sign you input sort of matters there. Anyway, the way to think about these, there's actually, this is not entirely pointless. It actually comes up, you can think about it in terms of matrices or sort of a more general geometric form. So with a square of side x, you can think about that in a couple ways. You can remember then that x squared is equal to up triangle x plus down triangle of x. It just so happens that up triangle of x is equal to x plus down triangle of x. So the diagonal itself is typically of similar order in a matrix as the side, so you're not necessarily thinking about length here. And then you have what people consider the upper and lower triangular parts of the matrix. The number of elements in an x by x matrix is for either upper or lower triangle is given by this down triangle of x. If you add x to down triangle of x, you get up triangle of x. And if you add up triangle of x and down triangle of x together, you will get x squared, right? X squared. Okay, so I realize this probably seems super simple and pointless and probably not interesting at all, but when you start looking at weirder algebras, things stranger than imaginary numbers, these operations I think might be useful. And they come up in a lot of contexts. Most people just happen to leave them in some algebraic form so that you don't really think about them too much. But they're there, they're in math all over the place. I assure you, if you look for them, you will find them.